Electromagnetic induction. Under this topic, we'll be discussing what is electromagnetic induction and what are the laws governing electromagnetic induction. Then we'll be explaining about the magnetic field, which is represented by 5B. Then, based on that, what is Faraday's law and Lenz's law. Then I'll be explaining about the eddy current. Then there are various methods to measure or various methods of inducing EMF. So various methods of inducing EMF. Then we'll be explaining about the self-induction. And then mutual induction. And then what is the coefficient of self and mutual induction. Then I'll be explaining about the solenoid. Then there is a concept called the coefficient of coupling of two coils. Then we need to know something about the non-inductive winding. Then I'll be explaining about the devices. The devices based on EMI. The devices based on EMI. Then we should know something about the AC generator. Then transformer. And then under which we should know the principle of transformer. Then we should know about the losses in transformer. Then we should discuss the ways to minimize the losses in a transformer. But this topic can be totally covered in three aspects. One is Faraday's law, then Lenz's law of electromagnetic induction. Secondly, self-induction and mutual induction. And then AC, generator, and transformer. So these are the major parts we'll be discussing. Excuse me. Now let us go to the Faraday's law. Faraday's law of electromagnetic induction. Magnetic flux that can be represented by phi b. It is the number of magnetic field lines. It is the number of magnetic field lines passing through a given surface. Normally, that is perpendicular. Let me consider. So this is x-axis, y-axis, z-axis. Let me consider this xy plane. So let me call this as xy plane. So the number of magnetic field lines passing through the given surface means assuming that xy is the plane, so through which how many lines are passing? Are you able to follow? Perpendicularly to the plane. So this is the magnetic field lines. So this is the surface area which is perpendicularly this magnetic lines are passing. And you know very well from north to south the magnetic field lines are passing, and the magnetic field strength is indicated by B. So B is the magnetic field, or it can also be called field strength. And let me discuss. I am taking a very small area like this, very small area. So this can be called ds, very small area. So area element. So what is ds? ds is area element, small area. So in that small area, how many field lines are passing? That can be d phi, magnetic flux element. What is that? Magnetic flux elements. Now we can define this d phi as the magnetic field strength. How much it is that as a vector magnetic field dot ds, the small surface area element. So this is actually a dot product because B vector is the magnetic field vector. And what about ds, surface area element vector? Okay, surface area vector element. So this results what you know already, that is a vector dot b vector is equal to a vector modulus into B vector modulus. Modulus means we consider only the magnitude into cos of the angle between them, theta. So in this case, the d phi can be, let us expand it as magnitude of vector B, means simply B into ds and cos theta, where theta is the angle between what? The magnetic field and the surface area element. Now, electromagnetic induction. And in fact, you should know the SI units also. And you know very well this d phi being the scalar product is the scalar quantity. And what about the magnetic unit of magnetic flux? My unit of magnetic flux or magnetic field in this case, it is what? That is, let me consider the that is as Weber. Okay, so it means the magnetic flux is Weber. Okay, take down Weber WB. So 1 Weber is equal to 1 Tesla meter square. Okay, Tesla meter square. And here I will put the phi because I'm talking about SI units of magnetic flux. So since the magnetic field unit is here Tesla and this is meter square, so Tesla meter square, that is called 1 Weber. Okay. Now electromagnetic induction. It is the phenomenon of inducing an EMF, electromotive force, due to the change in magnetic flux with the coil, linked with the coil. So change means d phi b. And actually speaking, how fast it is changing, then you can call it d phi b divided by dt, or simply you can call it d phi by dt, because electric flux is indicated as phi e, magnetic flux is indicated as or represented by phi b. So in this case, we are going to discuss in detail about the magnetic flux. So let me identify this as d phi by dt. According to Faraday's law of electromagnetic induction, let us consider two laws. First law. Second law. First law states that whenever the amount of magnetic flux linked with the coil, I must say that is magnetic flux associated or linked with the coil. So whenever the amount of magnetic flux linked with the coil changes, an EMF is induced. So this is the first law. So initially we say there is an EMF. That is because of the change of what d phi b. This is the first law. And this EMF continues till the change happens. When there is no change, there is no magnetic induction. I mean, electromotive force induction. No induced mode, EMF. Okay, so no change in phi B means what? That is no EMF. So this EMF can be represented as E. So in the second law, the magnitude of this EMF, when I say magnitude, we can put modulus also. Okay. So the magnitude of the EMF is proportional to, according to the second law, directly proportional to the rate of changes. When you say rate with respect to time, any change taking place with respect to time can be called rate of change. Here, rate of change of magnetic flux. So you can call it d phi b by dt. Don't mistake that it is a d phi into b. This is wrong. Okay. This is d phi at b. That is magnetic flux change. That is how fast the magnetic flux is changing with respect to time. So here you know very well this is nothing but magnetic flux. So you can introduce the proportionality constant that is called K here. So d phi b divided by dt is equal to induced EMF. And here this is the induced EMF. EMF magnitude of induced EMF when you put like this. Magnitude of induced EMF. So when K is equal to 1, this modulus of that is magnitude of induced EMF is equal to d phi by dt. Then later Lenz he corrected the Faraday's law and introduced the minus sign. So he said this induced EMF is equal to minus d phi by dt when K is equal to 1. So this negative sign is very important. So this indicates the direction of induced current is such that it will oppose the cause which has produced it. Is such that it will oppose the cause which has produced it. Then eddy current. Eddy current, in fact, these are the currents produced by here the currents are produced, or you can call it induced also. Currents induced. Why I have given in plural so many currents? Eddy means swirling, water swirling, நீர் சூழல்னு சொல்றாங்க அப்படி சுத்தி சுத்தி அடிக்கும். For example, washing, take washing machine where you can have the swirling action. Okay, so like this. So this kind of eddy currents. So likewise, there are so many swirling of currents produced in the body. It is induced in the body of metallic mass. When the magnetic flux threading through them changes. For example, you got a coil like this, and can you wind the coil like this? You need some solid core inside. Okay, and that is because of the solid mass, there will be a lot of what? Eddy currents produced or induced. So the key word here is small currents of a swirling nature, you can call it. Swirling nature means sural mari, chutti chutti. In the solid body around which the coils are wound. So when the magnetic flux going on changing, this kind of eddy currents are induced inside the coil where you have got the solid mass of metal. Next. And there are so many applications of these eddy currents. We'll discuss later about this. And you should know the disadvantages of eddy current. And before that, we'll try to understand the current, the amount of current produced here. So this current I is equal to the induced EMF divided by R, the resistance. And this induced EMF is nothing but d5 by dt. So this is d5 by dt divided by R. Disadvantages of eddy current. First point, eddy currents cause unnecessary heating. And that heat may damage the insulation of coils. So usually you got a lot of coils wound around the iron core, and when they are tightly packed or coiled, they touch each other. And in order to avoid conductance between these coil, they put some insulated varnish over that. Are you able to follow? So when heat produced will definitely affect this insulated coil, and thereby it damages the coil. Okay. Next, second point, the excessive heating may lead to fire also. So it will lead to financial loss. Okay, and also hazardous. Then eddy currents can reduce the efficiency of machines because they try to destroy the relative motion. So these are the disadvantages of eddy current. Now let us see how we can minimize the eddy current. It can be reduced to some extent by cutting narrow slits in the body of the metal. So it can be reduced by narrow slits. By narrow slits. Means instead of putting the solid metal, what you can do, you can give a slotted metal like this. Are you able to follow? You can cut. So this is the slotted metal or cut metal. We'll be having a lot of slots. So that will reduce. And the more effective method is by using laminated core. Laminated core instead of solid mass. For example, and that is why you could have seen in some of the uh, that is transformer this kind of stacks of sheet metals like blades stacked one over the above. Okay, so instead of keeping one solid metal, you can have the small plates of metal, sheets of metal, one over the above. Okay, so that is stacked, like placing razor blades one above the other. Okay, and it will be having slots also very effectively. So this is called lamination of sheets. So laminated core around which you can wound the coil. Are you able to follow now? Okay. So the plane of the sheets are placed, the plane of sheets, such sheet are placed perpendicular to the direction of current. Perpendicular to the direction of current. That would be set up by the induced EMF. Or the plane of sheet can be parallel to the magnetic field. One is this idea, perpendicular to the direction. Second is parallel to the magnetic field direction. So either way we can keep it. So if it is kept perpendicular, it should be perpendicular to the direction of the current set up by the EMF. Otherwise, parallel to the magnetic field direction. Okay. So these are the two ways with which we can reduce the eddy currents. Now, let us discuss some of the important applications of eddy current. Application of eddy currents. It is used in induction furnace. See, in this world, nothing is waste. Anything can be exploited in a suitable way. For example, it is producing heating, it is producing heating. When you say the same heat can be produced to heat other materials. So it means it can be used as this phenomenon, this eddy current effect can be used as what? A heater. And that is why we got induction stove and then induction furnace. Okay, take down. So induction furnace, especially for melting metals. So for melting metal means there is in such a way you are developed huge heat. So the metal specimen is placed in a rapidly varying magnetic field so that large eddy currents are set up and a large amount of heat produced will definitely melt the metal. So in such a way we can construct and design a induction furnace. So you've got the coil like this and now you can place the metal and enormous amount of heat is produced and that is molten, okay, into liquid, molten metal, right? Because we see that is it forms what lot of eddy currents like this, swirling action. So these are the eddy currents and these current eddies that causes the what? Heating, and that heating can be effectively utilized this metal to melt it, to melt the metal. Okay. Next point, next application. Electric brakes in train. So on applying brakes, a strong magnetic field is set up. When you apply brake, strong magnetic field is set up. And this is attached to the drum, to the rotating wheels. rotating wheels. The eddy currents are set up in the drum and exert a torque. So this causes a torque. So this torque is, a strong um, magnetic field produces torque, and this torque is applied to the drum so that the train can be stopped. Next, third one, electromagnetic damping. Electromagnetic damping. Damping means, for example, that is when you've got a balance like this, your 2 point balance, and there will be a pointer here. So you could have seen that the vegetable vendor, he tries to arrest the oscillating needle so that he forces the balance to come to the rest. So such kind of arresting the oscillation, that is called damping. So arrest the movement. And you've got the galvanometer, and it shows the reading, and it goes on oscillating, means it would be difficult for you to measure the current, right? So in order to arrest the oscillating needle, you can apply this eddy current so that it damps the galvanometer. Okay, so that causes uh, that is the meter, the galvanometer rotates due to the current flowing through it, and the eddy currents are set up in the metallic core. So the eddy current, they are of opposite nature, so the rotation of the coil can be arrested. Third, next one, speedometer. In speedometer, it is used to record the instantaneous speed of the vehicle. Instantaneous speed of vehicle. A magnet is kept. A magnet is placed inside the aluminum drum. So here you have to keep the magnet. A magnet is kept inside the aluminum drum that rotates with the speed of the vehicle. That is, let me say this is the wheel, so it is rotating. The eddy currents are produced. The eddy currents are produced in the drum. It will form the eddy current. Okay, it is produced. Eddy current. Eddy means, as I already told you, the swirling current. So this, for example, the wheel is moving in this direction. The eddy current will be moving in this direction. so that it will try to arrest the motion of the wheel. So this produces a torque acting on the drum. The, the torque acting on the drum in opposite direction. So through an angle, so this depends on the speed of the vehicle. So thereby we can record the speed of the vehicle instantaneously. Finally, this is used in electrical energy meter. Electric energy meter or electric power meter. You could have seen that this is the meter where you can see some kind of rotating disc. So the metal disc in electric energy meter rotates. This is rotating. You could have seen. Have you ever seen I mean, this kind of rotating disc in your energy meter, that is power meter? You should go and see in your electrical box. So where you can see the meter and you can see the rotating disc. It will be rotating like this. Okay. So here the eddy currents are produced or induced by the magnetic field produced by the AC fluid. For example, how much current is produced? So this is the input and this is the output. So current you are taking and current consumed. This is supply and this is the power meter. So based on the current and it will produce the magnetic field, and based on the magnetic field it will rotate, and based on the rotation the current can be monitored. Okay. So we have discussed various methods of application, various applications of the eddy current. Now let us discuss about the EMF, the methods to produce EMF. Take down methods of inducing EMF. There are three methods. One is by changing the strength of the magnetic field. Another is by changing the area of the coil placed in the magnetic field. Third is by changing the orientation, that is theta. So you can change the dB or dA. Magnetic field can be changed, area can be changed, theta, the orientation can be changed. So this is the orientation change, this is the area change, and this is the magnetic field change. So by these three methods, you can produce the induced EMF. Now let me see the motional EMF. Let me consider a coil U-shaped loop where I have kept a moving rod PQ. is a moving rod. RS is the another end. Now this is the loop. And the area of this loop can be changed by the moving rod. So PQ is a moving rod. So by keeping the rod at this position, this position, this position, the area can be altered. Okay. So that is the idea of introducing the area. By changing the area, you are able to introduce and induce the EMF. So this PQ is of length L, length of the rod, and the induced EMF is equal to how much magnetic field is applied and what is the length and how fast the rod is moved. That is the velocity of the rod. Okay. So when the area of the coil through which the magnetic field passing is changed by moving the coil into or out of coil. So this side or this side. So that this area can be altered. Are you able to follow? So this is the area enveloped by the coil A. So this can be altered as a dA. So by changing this, you are able to get the individual of how fast it is getting changed. So that is also very important. Next, R is the resistance of the loop. We know Ohm's law, according to Ohm's law, V is equal to IR. So in that case, I is equal to what? That is V by R. So in that case, we can put I is equal to E by R. That is the induced EMF. So this is nothing but the voltage. And here voltage induced electromotive force voltage. And this is given by E is already given as BLV. So you can put the BLV divided by R. Therefore, I is equal to BLV divided by R. Here the into mark represents the magnetic field direction. Okay. So moving upward vertically. The direction of current will be clockwise. So that is determined by the Lenz law. Now let me consider this a PQ, that is a moving rod. This moving rod PQ moves towards left like this. So the area of the loop hence will be changed, is it not? So it will reduce, it will decrease, right? Initially it was like this, huge area. Now it is coming left. So the area is reduced, area is decreased. So the induced current would try to increase the flux by magnetic field, inducing magnetic field. in the direction of the applied field. And that is why it is in the clockwise. Clockwise direction means in this direction. So let us consider the force experienced here, F, is equal to V into I into L into sine of theta. So here it is perpendicular, so I can put sine 90 degree. Okay. And what is this I? We already discussed. What is this I? I is equal to BLV by L. So we can substitute this I by this equation, right? So that you are able to get V into BLV divided by R into L into sine 90, it is 1. Therefore, the equation becomes BB V squared LL L squared V divided by R. So what is B? Magnetic field. L, length of the rod. V, how fast the rod is moved, right? Or the resistance. Now, to move this conductor, the power is the move the conductor to move this conductor. The power supplied by the external force. Is it not? We have applied the external force, right? So to move the conductor, in this case, the rod, right? So the power is applied externally. The power is applied or supplied externally. So it means it has got certain amount of force with certain velocity it has moved. Okay, so FV. So this equal to power. This P is equal to FV. Now we can replace this. So instead of F, we can replace this. So therefore, P is equal to what? What is the value of F? V squared L squared divided by R into V means V into V squared. Are you able to follow now? So P is equal to what here? V squared into L squared into V squared by R. Now we have got another equation. Power is nothing but the EMF and what? There is a voltage here induced EMF into current. So this power is dissipated as heat. Is it not? This power is dissipated as heat. Dissipated means leaked. Or move. Leaked means dissipated. From the body, it is coming out. So dissipated as heat, developed as heat, and coming out as heat. So this P is equal to E into I, and this E is nothing but this E we already taken as how much BLV, is it not? That was the initial equation here. Induced EMF is equal to BLV. So we can put this BLV, okay? into I. And this I is, what is that I? Here we have BLV by R. So BLV by R. So what we have taken E is equal to BLV and R is equal to what? BLV by R, right? Okay. So it means that is equal to B squared, right? L squared, V squared divided by R. That is also P. So from this, it's clear that this is associated with the mechanical energy. This is associated with the electrical energy, right? This is because of the movement. This is because of the electrical consumption. Therefore, the electrical energy is produced at the cost of mechanical energy. What do you understand from this? That is, mechanical energy is converted into electrical energy, and these two energies can be interdependent. So, we can easily calculate the amount of energy passing through the electrical, I mean, passing through the wire. The current passing through the wire can be easily monitored by the rotating disk, and that is applied here in the case of eddy current also. This should be called I. Okay, so that we can substitute here. So I have wrongly given here. This is not R, this is I. So I is equal to BLV by R. So that you can substitute E and I. Okay.